Before starting, put the auto-generated YouTube subtitles in French or your mother tongue to get everything, and slow down or speed up the pace as needed. If you don't have time to watch it, just listen this video as a podcast while doing something else. Now listen and learn English as exploring our world. Have you ever stood outside on a clear night and looked up? The sky becomes a breathtaking canvas, filled with countless stars, each a distant sun. Our galaxy alone holds billions, and there are trillions more galaxies beyond. With so many worlds, why does the universe seem so quiet? The universe should be teeming with life, yet when we listen, we hear only silence. This is the Fermi paradox. With so many stars and planets, where is everybody? As we search the cosmos, Fermi's question echoes louder than ever. The search is on. In 1950, over lunch at Los Alamos, Enrico Fermi asked a question that still echoes today. But where is everybody? The Fermi paradox wonders why in a vast ancient galaxy we see no sign of other civilizations, only silence. This great silence remains one of science's most profound mysteries. The Fermi paradox asks, with billions of stars and planets in our galaxy, why haven't we found any signs of intelligent life? There are hundreds of billions of potential homes for life. Many could be Earth-like. Yet we've found zero evidence. The universe appears empty and silent. The search for aliens becomes a cosmic detective story, one with the highest possible stakes. The Fermi paradox isn't just a puzzle. It's a framework for searching for life. Its possible answers fall into three groups. Maybe we're alone, maybe others are out there but hidden, or maybe civilizations destroy themselves. This paradox pushes us to ask better questions and search the universe with purpose. For most of history, planets around other stars were just a guess. But in 1995, astronomers found a planet orbiting 51 Pegasi, opening the floodgates. Now we know there are thousands of exoplanets. Planets are normal, not rare. Our galaxy is packed with worlds, and the search for life is more exciting than ever. The thousands of exoplanets we've found are way stranger than we ever expected. Hot Jupiters, super-Earths, even diamond planets. Nature's imagination is wild, and every new world is a clue in our search for life beyond Earth. With billions of worlds out there, some are bound to be a lot like ours, and that's what makes this search so exciting. Discovering an exoplanet is one thing, but figuring out what it's actually like is a whole new level of challenge. For years, we could only measure a planet's size, mass, and orbit. This gave us clues about its density, telling us if it was likely rocky or gassy, but it revealed nothing about its potential to harbor life. To truly assess a world's habitability, we need to know what's in its atmosphere. The atmosphere acts as a planet's fingerprint, containing chemical clues about its climate, its geology, and most importantly, whether biological processes might be at work. Getting a glimpse of these distant alien skies has long been the holy grail for exoplanet hunters. That holy grail is now within our reach thanks to the unparalleled power of the James Webb Space Telescope, or JWST. Launched on Christmas Day in 2021, JWST is an infrared observatory of unprecedented size and sensitivity. It uses a technique called transmission spectroscopy to study exoplanet atmospheres. When a planet transits its star, a tiny fraction of the starlight passes through the edge of the planet's atmosphere. Different molecules in the atmosphere absorb specific wavelengths of light, leaving a unique chemical signature imprinted on the starlight that reaches the telescope. JWST is so powerful it can decipher these faint signatures from trillions of miles away. In its first year of operations, JWST has already delivered spectacular results. It has confirmed the presence of water vapor in the atmospheres of several exoplanets, a crucial ingredient for life as we know it. It has also detected other important molecules, including carbon dioxide, methane, and sulfur dioxide. These discoveries are helping us piece together the climate and chemistry of these alien worlds. For example, finding both methane and carbon dioxide could suggest the presence of geological activity, like volcanoes, which can be vital for regulating a planet's long-term climate and recycling essential nutrients. Another key feature for sustained habitability on a world like Earth. The ultimate goal is to find a biosignature, a combination of gases that is difficult to explain without the presence of life. On Earth, The combination of abundant oxygen and methane in our atmosphere is a giveaway sign of biology, as these gases would normally destroy each other without being constantly replenished by living organisms. Finding a similar chemical imbalance on a distant exoplanet would be the most profound discovery in human history. While we are not there yet, the James Webb Space Telescope has given us the tools to begin this search in earnest. For the first time, we are not just counting worlds, we are beginning to read the stories written in their skies. To find life, we look for planets in the habitable, or Goldilocks zone, where it's not too hot, not too cold, but just right for liquid water. Too close to the star, water boils away. Too far, it freezes. But in the Goldilocks zone, life has a chance to begin. This is our first step in narrowing the vast universe to worlds where life might thrive. Being in the Goldilocks zone is just the start. A habitable world also needs a protective magnetic field, active plate tectonics, a stable star, and the right size to hold an atmosphere. All these factors must come together to create a true cradle for life. Of all the ingredients for life, liquid water is the most essential. Every known organism on Earth depends on it, and its unique properties make it the perfect medium for life's chemistry. That's why the search for habitable worlds is, at its core, a search for water. When telescopes like James Webb detect water vapor on distant exoplanets, it's a major clue that life could be possible. But water alone isn't enough. Life also needs time. Evolution is slow, requiring billions of years of stability for complexity to emerge. So the real challenge isn't just finding the right place, but finding a world that's been right for a very, very long time. In 1961, Dr. Frank Drake created a simple equation to estimate the number of communicative civilizations in our galaxy. The Drake equation breaks the big question, are we alone, into smaller, answerable parts: star formation rates, planets, habitability, life, intelligence, technology, and longevity. Each term narrows the odds, guiding us from billions of stars to a final estimate, n. The equation isn't about precision, it's a tool to organize our ignorance and focus our search. Thanks to modern telescopes, we now have real data for some terms, like the number of stars with planets. The Drake equation transforms a cosmic mystery into a scientific roadmap, showing us where to look and what to ask next. It's more than math, it's a framework for our curiosity about life in the universe. Let's walk through the Drake equation with what we know. Star formation and planets are common. Almost every star has planets, and many have worlds in the habitable zone. This makes the galaxy seem full of potential for life. But as we move to biology, how often life starts, how often intelligence evolves, we hit unknowns. Earth is our only example, so we don't know if life is common or a fluke. If you're optimistic, the galaxy could be teeming with civilizations. If pessimistic, we might be alone. The final answer swings wildly based on these assumptions. The silence of the sky could mean we're rare, or just not listening in the right way. The last term, L, is the lifespan of a communicating civilization. Even if life and intelligence are common, civilizations might not last long. We've only been sending signals for about a century, a blink in cosmic time. Natural disasters or self-destruction could end a civilization quickly. If L is short, the galaxy could be filled with extinct cultures, explaining the silence. If L is long, ancient civilizations might still be out there. The Drake equation forces us to ask, can intelligence survive its own power? For over 60 years, SETI has listened for signals from other civilizations, focusing on radio waves, an efficient, logical choice for interstellar communication. Early searches targeted the water hole in the radio spectrum, a symbolic spot linked to life's essential ingredient. Giant telescopes scan the sky for narrowband signals, artificial beacons that would stand out from natural cosmic noise. So far, we've found only silence. But our search has barely scratched the surface. We've sampled a tiny fraction of the possible stars and frequencies. the absence of evidence isn't evidence of absence. The search continues, driven by the hope that one day we'll catch an echo from another mind. While listening for deliberate messages remains a cornerstone of the search, scientists are now expanding their methods to look for more subtle clues. The new frontier is the hunt for technosignatures. This is the search for any observable evidence of technology on a galactic scale, whether it was intended to be found or not. A thriving, advanced civilization would likely alter its environment in ways that could be detectable from light years away. We're no longer just listening for a hello, we're looking for the indirect fingerprints of alien industry, engineering, and energy consumption. This approach broadens the search, since a civilization might exist for millions of years without ever sending a deliberate beacon our way. One of the most exciting types of technosignature we're looking for is atmospheric pollution. An industrial civilization, much like our own, might produce artificial gases that wouldn't occur naturally. Chemicals like chlorofluorocarbons, CFCs, which we once used in refrigerators and aerosol sprays, are powerful greenhouse gases that could potentially be detected in an exoplanet's atmosphere by the James Webb Space Telescope. Finding such industrial pollutants in the sky of a distant world would be a stunning sign of technological activity. It would be like finding a plastic bottle on a deserted island, a clear indicator that someone else was there, leaving behind the byproducts of their existence. Another fascinating possibility is the search for massive alien engineering projects. A truly advanced civilization might need staggering amounts of energy, way more than a single planet can provide. To meet these needs, they might construct a Dyson sphere or a Dyson swarm, a megastructure of solar panels built around their entire star to capture a huge fraction of its energy output. While such a structure would block the star's visible light, it would have to radiate waste heat as infrared light. Astronomers are now scanning the sky for objects that are unusually bright in the infrared but dim in visible light, a potential sign of these colossal stellar engines at work. We're also beginning to look for simpler signs, like the glow of city lights on the night side of an exoplanet. As a planet rotates, we might be able to detect a subtle change in the light it reflects if one side is covered in artificial illumination. Other potential technosignatures include the heat island effect of sprawling urban areas, or the glint of light off massive arrays of solar panels in orbit. Each of these methods moves beyond the need for aliens to be actively trying to contact us. Instead, we become cosmic archaeologists, searching for the passive, unintentional signs that a civilization is living and breathing on another world, just going about its daily business. Humanity dreams of exploring exoplanets up close, but the distances are staggering. Our fastest spacecraft would take thousands of years to reach Alpha Centauri. Breakthrough Starshot aims to send tiny probes with light sails, pushed by lasers, reaching 20% the speed of light. These nanocraft could send back our first close-up images of another world, redefining our place in the universe. For years, we searched for life only in comfy, Earth-like places, but discoveries of extremophiles, microbes thriving in boiling acid, deep ocean trenches, and even nuclear reactors changed everything. Life isn't fragile. It's tough, adaptable, and might thrive in the most extreme places, even beyond Earth. Extremophiles have totally changed how we think about the habitable zone. Life doesn't have to be on a planet's surface. It can thrive deep underground or beneath ice, powered by heat from within. This means even frozen worlds or rogue planets could hide oceans and life, expanding our search for habitable worlds far beyond what we once imagined. Extremophiles on Earth have inspired us to search for life in our own solar system, on Mars, Europa, and Enceladus. These worlds may hide oceans or underground habitats, offering hope that life could exist beyond Earth. The search is closer to home than we ever imagined. As we search the silent cosmos, we face the Great Filter, a barrier that may explain why the universe seems empty. Is this filter behind us, making us rare victors, or does it still await us, a warning for our future? The empty sky forces us to reflect on our fragility and the challenges ahead. Maybe the galaxy is quiet because we are among the first. On the cosmic clock, humanity has only just arrived. We might not be late to a party, but the very first guests. If so, we are the galaxy's nascent consciousness, its great hope for the future. The search for life beyond Earth is a mirror, reflecting our hopes, fears, and curiosity. It unites us, pushing the boundaries of science and imagination. Whether we find cosmic siblings or only silence, the journey changes us. In searching the stars, we discover ourselves.